Hello, welcome to my presentation. I'm SungKu Kang from the Department of Civil and Environmental Engineering at Northeastern University. Today, I'm going to talk about the research on topology optimization of Tetris via physics-guided deep Q-learning, which is a type of reinforcement learning. In this presentation, I will present how stonemason design can be optimized via state-of-the-art technologies used for Tetris AI. This research is performed under the supervision of Dr. Michael Kane and supported by Ru Institute of Experiential AI at Northeastern University. First of all, let me talk about the motivation of this research, which is two important considerations for sustainable construction ecosystem: embodied energy and resilience. First, embodied energy is the energy consumed to produce and transport the material. On the left side of the slide, it is shown that it takes about 2.9 quadrillion BTU to produce the construction material, which takes significant portion of US energy consumption and CO2 emission. Another thing is about the resilience of construction ecosystem, which can be improved if we can properly utilize local materials for rebuilding. Given the two considerations, proper material selection is the key to improve the sustainability of construction ecosystem. This slide shows the plot of embodied energy versus the strength of the materials. We can see that metal and plastic generally have higher embodied energy, while natural stone and concrete bricks have lower embodied energy, which makes masonry as a meaningful option for sustainability. In the meantime, the advancement of robotic construction is expected to improve the efficiency of masonry construction, as it can eliminate labor-intensive work such as bricklaying shown in the slide, especially if the robotic technology can automate natural stone masonry will become an even more attractive option for sustainability, as natural stones have higher strength with lower embodied energy. However, there are two main challenges in design for stone masonry. First, unlike brick masonry, stone masonry design requires highly domain-specific knowledge due to the variability of natural stones in terms of their properties and shapes. It is a significant challenge as the knowledge on stone masonry has been waning for several decades. Second, while current topology optimization has been successful with homogeneous materials, its effectiveness is not guaranteed for stone masonry design, where heterogeneous natural stones and the interaction via joints need to be incorporated. For example, the three shapes shown in this slide may yield significantly different structural behaviors, regardless of the overall shape, due to the different organization of the joints between the blocks. In this context, the research question is, can we advance topology optimization for the heterogeneous materials and unit shapes, such as for stone masonry? To address the challenges, we focus on the analogy between Tetris and stone masonry. Specifically, both of them utilize heterogeneous blocks to form an overall structure, while their final performances are determined by the organization of the blocks. Inspired by this analogy and the success of the state-of-the-art AI to conquer Tetris game, we claim that Tetris AI can be adopted to solve stone masonry design problem in real time with proper modification. From the next slide, I will present how the problem is formulated and how the proposed framework works. This slide shows the formulation of stone masonry in the context of Tetris-like environment. On the left side of the slide, a simplified design problem is shown, which consists of 2D design space like Tetris board enclosed with the outer shell. One can freely place Tetris workpieces in the design space to design a masonry structure. And considering the boundary condition and external load applied to the structure, the behavior of the resultant masonry design can be evaluated with OpenCES finite element analysis, as shown in the right side of the slide. Given this formulation, the objective is to minimize the weight of the structure M, which can be represented by the number of coordinates occupied by the blocks, while satisfying the required design safety factor based on ultimate stress limit state, which can be derived with structural analysis. This slide shows an overview of the proposed DeepQ learning framework, which is a type of reinforcement learning framework. The framework consists of gaming environment, DeepQ learning agent, experience replay, and structural analysis module. Let me introduce one by one and how the framework works. First, the gaming environment defines the state of the Tetris board, represented by the organization of the block, and the action to place each block inside the board, which also represent the transition between one state to another state. It also defines the reward based on the structural analysis, which makes an AI agent to maximize the reward by continuously playing Tetris-like games. It should be noted that the reward is not calculated during this exploration step, as the calculation of the reward can introduce unexpected bottleneck from structural analysis when multiple sessions run in parallel. Next, the experiences obtained from the environment during the exploration are stored in a data buffer called experience replay, and random batches of sequential experiences are retrieved in each iteration to train DeepQ learning agent. And before feeding the experiences to the agent, the rewards are calculated with OpenCES. As mentioned, by not calculating the reward during the exploration, the framework can efficiently queue and calculate the reward in parallel. Lastly, the experiences are fed to the deep neural network of the agent, and gradient descent is performed to update the weight of the neural network. Here, the output of the neural network represents the expected cumulative reward, called Q value, when each action is chosen. Therefore, by continuing the exploration and training, an optimal action can be identified by choosing the action providing the highest Q value. From the next slide, I will present the experimental results. First, a simple design problem is tested under the same scale of Tetris game. In other words, for a 10 by 20 board using Tetris workpieces. Here, the vertical pressure of 1 megapascal is applied, and the masonry should have safety factor higher than the threshold of 2. While the problem seems simple, identifying an optimal design is time-consuming as it involves too many number of states. 24 hours of exploration with a high-performance computing node with 36 AMD EPYC CPU cores have been performed with 50 repetitions, and the result shows that the rewards are continuously increasing. And the resultant structure are gradually becoming lighter while satisfying the safety factor threshold. The final design, the structure with 2 columns, is expected to be the optimal solution, as we confirmed that lighter designs could not satisfy the safety factor constraint. And to test the extensibility of the framework, a slightly more complex design is also tested, where horizontal pressure is also applied on top of the structure, which represent seismic load via ground movement. And it also allows smaller workpieces to form the structure. The results with 25 repetitions show that the framework could improve the reward as it explores, but it is shown that the stability is not as good as that for simple problem within 24 hours. However, it should be noted that the framework could gradually form more and larger cavities, and it also introduces arch-like patterns to satisfy the safety factor while minimizing the weight of the structure. And this is the close-up of the resultant design, and it is shown that it jointly utilized different sizes of blocks to form arch-like patterns of various sizes, which demonstrate the design capability of the proposed framework. In the next slide, I will summarize today's presentation. For sustainable construction ecosystem, stone masonry can be an attractive option, as natural stone are low carbon material with low embodied energy. However, the variability of natural stones makes it difficult to current topology optimization to provide an effective design. To address the issue, a DeepQ learning framework, a type of reinforcement learning framework, is developed inspired by Tetris AI, and its feasibility and extensibility are demonstrated. Future work lie in improving the stability of the framework, introducing random queue of natural stones, and increasing the resolution of natural stones, such that the framework can be applied to practical stone masonry design. Before I finish, I would like to acknowledge the support from the Ru Institute of Experiential AI at Northeastern University. Thank you very much for your attention.